Okay. Hello. This is the homework solution video for the second booklet, second lesson of module 5, and this is on circular motion. Okay, so let's get to the multiple choices. All right, the first question says a 2,000 kilogram vehicle drives around a circular bend on a horizontal surface at 50 meters per second. If the radius of the bend is 20 meters, the magnitude of centripetal force acting on the car. Uh, so yeah, this question just gives you like all the important stuff that you need to calculate centripetal force. So this is pretty much just a substitute value question. So like centripetal force, if you recall, it's mv squared over r. Right, given the radius, given the mass, given the speed, substitute values, you'll get the answer. Question 2, an object with mass m travels in a circular path of radius r with a constant speed. The magnitude of the net force acting on the object is F. Another object with mass 2m, yada, yada, yada. So mass is twice, but then half the speed, okay, asking for the net force. So again, we know that undergoing circular motion, object has a net force equals to mv squared over r. That's just stuff revolving in a circle would do. Okay, this is net force. Okay, so now we notice how the mass is like twice, but the speed is halved. Okay, so let's for this type of question, let's do it in two cases. So we have like net force 1, that's equals to like m1 v squared, v1 squared divided by r, and then net force 2 is m2 v2 squared over r. But simultaneously, we also have this condition where so m2 is actually twice of m1. So let me just change that to 2 times m1, and also have v2 is like half of v1. So let's also change that to half of v1 and then squared. So if you open up the bracket, you get 2 times m1 and then 1 over 4 times v1 squared. Okay, now 2 times 1 over 4 is just 1 over 2. Okay, m1 times v1 squared over r. See how that's just like half of f1 of total force f1. So this is just a. Okay, so for all this type of question, just like make arrangements of two different forces, like different scenarios, change the variable, and then find a relationship, substitute the relationship, and then finally get your relationship. Okay, question 3. An object around a circular path, diameter 45 meters at a constant speed of 15 meters per second, angular speed. Uh, well, this is just recording this equation, right? And the substitute values gives the answer. Question 4, the frequency of an object in circular motion is 3.5 revolution per second. The radius of the circular path is 2.5 meters. What is the tangential speed v of the object? Okay, so this is pretty much just using v is equals to 2 pi r over t. Remembering that for uniform circular motion, the uh, period is conservative, it's constant, okay? And for a circle, the circumference is 2 pi r. The time it takes is a period. So distance divided by the time gives you the tangential speed. Question 5. A mass on a uniform circular motion completes 15 revolutions in a minute. Which of the following rows correctly shows the period and angular speed of the object? So 15 revolutions in a minute. We know that for one revolution, right? One rev is like so that's like equivalent to an angle of 2 pi, or like a change of arc length is r 2 pi r, right? So wants us to find the period. Okay, so this one, so 15 of this is like 1 minute. So we go, so like in terms of period, so we know that period is by definition like how many time for one revolution. Okay. Um, So this thing would be simply, okay, so we have 15 revolutions in a minute. So that means we have omega is equals to 15 times by the one revolution is 2 pi, okay, divided by the time, okay. in minutes. So it's just 60 seconds. Okay, so that gives you the angular speed. You end up getting this value. But how do I know the period? We also know that simultaneously we know that omega is equals to 2 pi over a period, right? So if you rearrange for your period, you will actually get the answer. Okay, good. Okay, and question 6. Student is investigating circular motion in a vertical orientation by swinging a bucket of water. This is a vertical circular motion, so not necessarily, okay, vertical circular motion does not necessarily correspond to a uniform circular motion because there is gravity. So that in this case, it says the minimum velocity, right, of the bucket, it must travel on the top of its circular motion to prevent water from falling out. Okay, so the water inside, they are kept within this bucket because of centripetal force, basically. Okay, I mean the bottom of the bucket must like supply this sort of pressure or this upward normal force uh, to supply the centripetal force required for the water to undergo circular motion so that doesn't fall out. Okay, therefore at the top, right? So the water feels a force downward mg that's just given by gravity. And then there's also going to be like a normal force from like the bottom of the bucket. Okay, so at the top, you have your sum of force is equal to mv squared over r, which is, okay, both towards the center, so m plus mg. And for that minimum velocity, we have n equals to 0. So it's just like the smallest velocity that is allowed for uniform circular motion. Okay, if the velocity is faster, yeah, sure, like you just have larger normal force. But if the velocity is like even smaller, okay, if it's smaller than the smallest velocity, you actually the water actually falls out because like mg is more than like enough to supply your centripetal equals to 0 is quite subtle here. It's quite subtle. Okay. So question 7, mass and speed of an object undergoing uniform circular motion shown as below. Radius of the circular path are also given. Magnitude of centripetal force is identical. Well, so centripetal force is proportional to m, inversely proportional to r, but quadratically proportional to v squared, to v, right? So so in this case, so that's a half, that's a 2, so like they just balance out, right? Wait, hold on. No, they don't balance out. Actually, let's just write it down. So for object 1, it's like centripetal force is just mv squared over r. For 2, centripetal force is half mv squared over 2r, so that's just 4. Okay, so they're not equal, definitely. 3 is 2mv squared, but this v squared gives you a 1 over 4 v squared over r. And that's basically 1 over 2. Okay. Okay, so none of these are equal. Hopefully 4 is equal to some one of them. This is m times 4v squared over 3r. Turns out that okay, let me just check my answer for 3. So this is 2. Half this becomes a 4. Actually, let me check my answer for 2. So this is half for the mass, and then this is so 2, this is which is 4, okay, 4 times v squared over 2r. Okay, yeah, it's that. Okay, so yeah, like you see how this 4 and then this thing stuff cancels out, and you just get mv squared over r. This is like the same as 1. So I made a mistake when I was doing 2. Okay, that's the answer. That's why it's like A, because 1 and 2 are the same. So yeah, guys, just be careful. Don't make a simple algebraic mistake. Okay, it happens, but like just be like careful. Okay, just know like you can check back your result. Always double check. Okay. So question 8. So the blade of an electric fan has a period of circular motion t seconds. When the centripetal acceleration of the outer edge is a, okay, so like The acceleration at the outer edge is like that radius gives you centripetal acceleration of A. Speed of the fan increase such that the centripetal acceleration becomes 4A. Okay, so we know that centripetal acceleration is giving us tangential speed over R. Okay, at this high speed, the period. Okay, so like we know that V is equals to 2 pi R over T. Okay, and squared over R. If I just expand the bracket, I'll get 4 pi squared R squared over T squared times R. So one of the R gets rid of, and then 4 pi squared R over T squared. So now if I change my acceleration to 4A, right, this means my period, okay, the radius is not going to change. I mean, the blades is not going to get smaller or larger. It's a physical thing, right? So that's not going to change. But if I increase my acceleration, I have to get faster. That means my period must decrease, right? So it gets faster. It takes less time to revolve in a circle. So I mean, this is 4A, right? So 4. Okay, so the first case is that. So now the next case is 4A, which is equals to that square over T square. Okay, so the correct way to do this is like to make a ratio, right? So this equation and this equation, they can divide. So 1 divided by 2, A cancels out, you get 4. And then the constant drops. Okay, this is the second case. Let's denote this as T naught. Okay, you're just gonna get T, so the original T squared over T naught squared. Okay, so now immediately you know the relationship. So the new T naught is equals to T over 2, right? So it's just 2 times shorter, right? So this is like half of it, so the time is 2 times as shorter. Okay, so that's fine. I mean, if you're pretty smart, from here that you know that's 4A, you can probably figure out T just from looking at the equation, yeah. But that introduces a lot of like chance for you to make mistakes. Okay, so what I recommend is like always to treat this question as like write 2 equations for different scenarios and then relate these 2 equations, finding the ratios. You can divide the equation, you can multiply the equation, cancel out the redundant, the spectator factors, right? Just get the relationship. Question 9. Conical pendulum. Okay, so the angle of the string makes with the vertical is. Let's try and find the angle. Okay, so with this question, you know the velocity, you know this mg here. You have a tension force. Yeah, so the best way to do this is to write equations for both directions, supplying centripetal force in the horizontal direction, and that's supplied by tangent. Oh, sorry, by tension horizontal component, which is t sine of theta. And net force on y is 0 because there's no vertical motion, and that's equals to t cosine minus mg. Okay, so from that you know that m times g is equals to t of cosine. And equation 1, equation 2, take 1 divided by 2, you get t cancels out, and then you get tangent theta, which is equals to v squared over rg. And substitute values, you can calculate your theta. Question 10. A stone is tied to a string and whirled in a vertical circle. Which of the following statement is correct? So A says that the speed of the stone cannot be a constant. Yeah, because there's gravity, right? So A is correct, but let's go through why B, C, D is incorrect. So the tension in the string remain constant. Not true, because like there's gravity, so in order to undergo uniform circular motion, tension changes. Right. So the strain is most likely to break at the top. Not true. Tension is most likely to break on the bottom. This is what we went through in class. So if you got any question, please ask. So the tension in the string and the stone weight always contributes to its centripetal force. Always contribute, not always, right? So the tension, actually the tension always, but the weight does not. Okay, so for example, the weight on the bottom actually it goes in the opposite direction as the required centripetal force. So it's like not even contributing. It's anti-contributing. It's like, yeah. So D is wrong as well. Extended response. The first question pretty much is the simple calculation, right? You just have to notice how in this case, the centripetal force of the car is supplied by a real force. In this case, it will be the frictional force. So friction force supplies the centripetal force. Calculate that. This is what being asked for question 8. Question B, explain why the same car must slow down to safely navigate to the circle. If the surface was to get wet. Okay, so I mean common sense, right? If you get wet, if the surface gets wet, it's like more slippery, and then the car must slow down, right? But in a more physical, like scientific explanation for this is you have to say that when the surface gets wet, it actually reduces the coefficient of static friction, right? So like this is like required. So in questions like this, you must mention something like this. Okay, you can't just say it gets slippery. That means nothing to a physicist. We must say something I must quantify. So it's basically a reduction of coefficient of static friction, causing that your friction force reduce, so that this thing reduces and no longer supplies the centripetal force at that velocity. Okay, so you must reduce your velocity such that the reduced friction is supplying. Okay, and then you can undergo circular motion safely. So yeah, that's just what it is. Okay, this question is pretty easy. You can pause the video if you wanna like, copy the answer down and just say. All right, so question 12. Question 12 is a conical pendulum, and this question again, try not to substitute values, try to substitute values at the end, derive the equation first, okay? Given the mass, given some dimension of this conical pendulum, it's given that the stringness, that's hypotenuse, and given the radius, that's this radius, which is a right angle triangle, so instantaneously you know the angle and you know this side as well. Actually, it actually is given, okay? It's not given. I mean, it's sort of given because you can calculate it. This is just like a 3, 4, 5 triangle, right? Pythagoras. This angle will be nasty, so I didn't explicitly calculate the angle. You can, but not recommended because you can just express all the like the trigonometric functions in terms of like a fraction. That's nice. And then the same thing, right? For all of this question, do net forces, right? Net force on y and net force on x, and then relate these two equations, rearrange it. Most likely, you're gonna get this, right? And then you end up substitute values to get whatever you want. Okay, so be careful. This question asks for both angular speed and tangential speed, so make sure you calculate for both. Again, box your final answer makes it more clear. So B says to show this equation. So show H is equals to G over omega squared. Deriving equation is a big skill to have for physicists. Okay, so let's do that. So from the equation above and the equation given here, tangent theta is R over H. And it's simultaneously equals to V squared over RG. Now inside V you get R times omega. So you get omega, and then you just rearrange for omega to get this equation. Okay. Question 12. Explain the effect on the angle that the string makes with the vertical when the velocity of the ball is doubled. Okay, so when the angular speed is doubled, okay, what I said is like the height h will be reduced by a factor of 4, right? As cosine theta is h over 4, okay? So the effect on angle will be something like this. The cosine theta will also be reduced by a factor of 4 as well, yeah, because you know angular speed is doubled. And from that equation, right, h is changed. H is reduced by a factor of 4, and in that equation, because h is changed by a factor of 4, theta will also be like decreased. We don't know exactly how much theta will be different, but we know how much like the cosine of that will be different. So you can quantify it by writing like an equation. We know that cosine is like monotonically decreased function for theta equals to 0 to pi over 2. So in this case, you have reduced your cosine function. That means your angle must increase. Okay. Yeah, something like this will be good. Okay. I mean, for this question, if you just said angle increase and you have some sort of understanding, you should be correct. Okay. Question 13. This is vertical circular motion. Yeah, so right, and so A says to compare the forces acting on the car at A and B. So this question is just basically write out the forces in A and B and then compare them, okay? And then there's like few points that you can do. So writing out the forces and making this judgment, the normal force judgment is 1 mark. And then talk about some like differences, three different comparisons, right? Yeah, just to say something else. So something like the normal force at A will be larger because it's literally like the direction of A is towards the centripetal force, but while mg is like against the centripetal force, and you end up getting like your normal force is like larger, and then at B is like similarly smaller. So that's one of them. So another thing that you can mention similarity as well, like gravity is the same, right? And also you can say that the required centripetal force is therefore larger rather than smaller, okay, due to conservation of energy. So like we know that car at A will be faster because it's lower potential, and car at B is gonna be slower because it's larger potential. So B says to derive an expression for the maximum velocity Vmax for the car to travel past point B without losing contact. So this is another example. Like all these questions with like maximum velocity, minimum speed, losing contact, yada yada yada. This tells you the normal force at that point is equal to 0. Okay. So yes, right on the point where you're about to fall, normal force is equal to 0, and just mg supplies all the required centripetal force at the top. So just do calculation, just do algebra. Okay. Question 14. Yeah, so bank track problem, pretty much the same as conical pendulum mathematical wise, just change the normal into a tension, right? So calculate the speed. Again, two directional forces, horizontal force supplies centripetal force, decompose your normal force. Normal force is horizontal component supplies centripetal force, vertical force is 0, and the n cosine balances with mg. Rearrange two equations, get that, and then substitute values, okay? So I start this equation because I want to use in the like next part. Question B, in normal circumstances, friction between tires of the car on the bank surface, they would contribute to our centripetal force, right? So if you draw this free body diagram, not only the normal and mg supplies it. This friction along the surface could be like up or down. I just draw it downward in this case because it has to be like one way, right? The other one would be like this way, but either way, friction force would have a horizontal component. Okay, like whichever way you want, there will always be a horizontal component which supplies centripetal force. Okay, so this question is a bit hard. It asks you to mathematically show that our like the the maximum speed is like larger if friction is also in place. Okay, so like with friction, right, you can go faster on this bend. It's kind of intuitive to think about it, but like how do you say it? How do you prove it using math? Okay, again, two equations, x and y. X supplies centripetal force, but in this case, you have to change. Previously, there's only n sine theta supplies it, but now we have a friction force. Let's assume it goes downward, right? If it's not going downward, it will be just like a negative sign, or this f is like a negative number. Doesn't matter. Let's assume it's positive. Okay, so yeah, and then this theta gives you like the horizontal component, so f cosine theta supplies it. And the vertical component as well, it's equal to 0, and n cosine minus mg, and then this extra term of friction going downward because that's a downward, okay? So if you were to write these two, I awarded 1 mark. And yeah, and then if you rearrange n from equation 2, okay, and then substitute back into 1, bit of algebra, bit of trigonometric identities, you end up getting something like this, right? So the centripetal force is mg tan theta plus f times sec theta. And if you rearrange for your v, you get this v max equals to this thing, okay? Now, compared to star, so star was like above. So my v was like rg10, square root of that. But now it's like v squared is equal to rg10 theta, but there's another extra term. And this term is larger than 0. Yeah? So, which means that in this case, with friction involved, you actually get a larger Mx, Vmax. Okay? So yeah, that just mathematically proves it. Okay. We even showed how much larger that you can go. Okay? So it's very, very good. Make sure you just like write your calculation along with sentences that describes, okay? Don't just write equations. Yeah, question 15. This is experiment question. So a rubber stopper with honor mass attached to a string, it's undergoing uniform circular motion. This weight here supplies mg, which travels by this string with a tension. That tension, which equals to this mg, supplies the centripetal force. So assume the rubber stopper undergoing horizontal circular motion, yada yada yada. Period is that. Calculate the mass. Okay, again, net force. Okay, we know that the net force is centripetal force. This is small m, which is the mass of the rubber stopper, times v squared over r, which is supplied by this big M times g. So it's very important for you to distinguish two different masses. Substitute v equals to 2 power over t. Get that relationship, rearrange for your mass. Because we don't know what v is, but we can calculate it. But my habit is never calculate anything. You only use calculator once in a equation. So substitute this value, right? Substitute the stuff with stuff that you know into this equation and give it off as that, okay? So yeah, pretty trivial. Next question. Question B, a different experiment, the rubber stopper is replaced with a 5 kilogram mass. The mass is attached to the bottom end of the string that remains unchanged. The new 5 kilogram mass is spun at such a way so that its radius remains constant. Okay, so now it's a heavier mass. Okay, previously it was like a few grams. Now it's like 5 kilograms. It's pretty heavy. It's kind of like the mass of your phone or something, right? So with a heavy mass, this gravity is actually going to sort of like drag our mass downward a little bit, so making it a conical pendulum. Okay. So what I said here is like a 5 kilogram mass weight has substantially greater weight force. So rather than a rubber stopper. So when the weight force is no longer negligible, that the string will make an angle to the vertical. So now like your whole model changes. So before it was like a horizontal circle, there's no like angle and stuff. Although that's still an assumption, right? Even though you have a very small mass, that mass still has like a little gravity that sort of drags it downward a little bit. It's because it's very small. For previous questions, we assumed it's negligible, but now the mass is not negligible. So it's going to give you a large angle. Yeah, so that changes everything, right? You have to remodel your equation and stuff. So now the centripetal force is provided by the tension. Yeah, but its horizontal component supplies it. Okay, so the tension is still equal to mg, capital M times g here. But now only a component of this applies the centripetal force. So now it's going to be less. Okay. So now the centripetal force provided by the horizontal component of tension, since mass at the bottom is constant, magnitude of tension remain constant. As a result, centripetal force is reduced. Okay. Right. Okay. Another thing is like by the way, just saying, okay, the vertical tensions balances with mg such that this thing goes into a conical pendulum. Okay. Right. Next question, question 16. Oh, this one is a monster. It's pretty difficult. Okay. So this one might not seem as easy, but if you understand energy and work with energy very fluently, probably it's not that hard anymore. Question A asks you to, so given that this you have this radius of this vertical circle, and you want to calculate, I don't know, this height so that it goes through the circle safely, right? Yeah, it's kind of hard. Imagine you're designing this entertainment facility for, I don't know, for like a park or something. Like, yeah, like you are the engineer. How, like, what height are you going to build this with so that the passenger are not going to fall down on the top, but they will like go through this. Okay. Yeah. Well, if you consider energy, right? So, I mean, this car gets velocity as it falls back down, okay? And then the velocity as it enters the circle determines how much height does it go. So the height actually calculates this velocity. So let's just do that, right? So consider work energy theorem. Instead of doing it at the bottom, let's do it at the top. So from this point P to point Q, there's like a okay, let me draw this straight. It's like a reduction in height, right? It's a change in height. Okay, so that reduction in height converts a little bit of potential energy into kinetic. So let's calculate it. By the work energy theorem, delta K is negative delta U from P to Q. Delta K is half M times V squared over minus U squared. Delta U, negative sign is here, right? Negative sign. Mg, difference in height. So this is like H of Q, which is final height, which is in this case is 2r, right? Minus just my h, right? So notice how we don't have any initial velocity, that's 0, okay? Like m cancels and all that, and you end up getting this equation. H final is 2r, h initial is just my h, right? So now we don't know, look, we don't know the speed and then we don't know the h. So this is like an equation that has two unknowns. Okay, one equation, two unknowns cannot be solved. But what we can do is we can rearrange. So we get this v squared right here. Still two unknown, there's like nothing we can do about it. I label this equation as 1. So we need to sort of like, this equation has two unknown, gives you like a hint that you need to find another one in order to solve it, right? So let's do that. Let's try and find another one. I mean, what other thing do we have is like, oh, we know that the object is undergo uniform, not uniform, but circular motion in this case. So why don't we just consider like the net force, right, equals to mv squared over r, see if it works out. So we know that at the top, there could be mg, then there is going to be mg, and then there could be a normal force, depends on my speed, right? Again, I want to find the minimum h, which means the minimum velocity here, so that passenger safely go through it. So I want that normal force equal to 0, okay? Another condition where normal equals to 0. So just sum of the force, mv squared over r, circular motion criterion, mg, and both normal and mg supplies it, but at the minimum speed n equals to 0. So I get v squared equals to rg. Okay, so this is another equation. Okay, this r should be a capital R. All right, my bad. Okay, it's the radius of the circle. And if you equate this v squared with this equation, you can therefore work out what h is. Okay, do some algebra, you end up getting h is 5 over 2 times r. This is actually very amazing because like you see how this height is only dependent to the radius of the circle. So it does not matter of how much the gravity is, or like how many passengers are on the cart, or the different mass of the cart, or something like that. It only matters with how large your circle is. So if you calculate your h, like okay, 2.5 times the radius of the circle, and then you move it to on the moon, right? And it will still be able to pass through safely. And you move it to the on the surface of like Saturn or something, I don't know. It will still like no matter the gravity, right? So this is independent of everything, only the radius of the circle. So it's kind of like an interesting result. Yeah, question B discusses that, right? So a physics student observed the motion of the roller coaster, makes the following statement. If there are more passengers on the roller coaster must start its journey from a greater height. Otherwise, they will not be able to travel past the circular track. Explain why the student statement is incorrect. So it's not correct because like I said, right, it's independent to the mass or the passenger number on the cart, right? It doesn't matter how heavy the cart is, it will still travel the same trajectory given that you have the same height, right? So like it's wrong because of that. You just mentioned this equation, right? But then if you're a critical thinker, like you can say that in ideal case, right, a more passenger means like the car is more heavy. That means it has a larger normal force. Like it has a larger normal force, like on the ground. So that means like if friction is like mu times normal, a larger normal force gives you a larger friction. So in ideal case, there's no friction. But if there is friction, there's larger friction, which reduces energy a lot, right? That means indeed, in real case, you actually need to have like a higher height just to account for that little extra friction, okay? Yeah, so this is my answer, okay? Just have a read of it. Question 17. Oh yeah, so this is like getting to little like atoms, right? So we think of atoms as electron orbits, the nucleus. I will learn this in more 8, but this is like part of it. Okay, so like electron orbits the positive nucleus in uniform circular motion. Just like use like with stuff that we're learning more 4, which is the electrostatic force. And that times 2 charges over r squared calculates the force between 2 point charges, which is the same thing as for atom in this case, right? So that force is like simplifying centripetal force. Calculate that force, and this force will be attractive because positive and negative charge. Part B is like, okay, So calculate the radius, right? So using this information, calculate the tangential angular speed of the electron. Okay, so given that the radius, and you equate with this, rearrange for your velocity to give you an answer. Okay, it's basically you have to know that this static electric force applies to the centripetal force. Remember that the centripetal force is always supplied by some real forces. Okay, and you end up getting this value. Question 18. If we refer back to question 14. Oh yeah, okay. Look, yeah, this question was like, look, so back to question 14, I derived this big thing. This is mathematically complicated. This was actually supposed to be done in a challenge question, but I just did it in this question. So yeah, so like originally for question B, what you guys should do is like probably like reasoning yourself without math, because like it's kind of hard to use this math in physics. Most students will just like argue themselves like, oh, this friction is like there's gonna be a component supplying the centripetal force. It's like an extra component compared to when there's no friction, and then so to argue away that it's gonna be a larger like velocity. But I just did it mathematically, so like this is the answer for technically for the challenge question. But I recorded it. So like we got that, and this is just larger, and we calculated the speed, right? So in this question, it actually tells you like the twice the speed. It gives you a quantification of like how much friction do you need, right? So with twice the speed, and only if you can derive this equation, you can therefore calculate the friction. If you have not derived this equation, this question is not doable. Okay, so that means it's so important for you to actually calculate, derive this equation out. Yeah. Question 19 is a pretty fun activity. Where like if you go to this YouTube video, you actually see a clip in Interstellar, where they're in a spaceship, and then the spaceship starts to rotate, and then that simulates gravity because the astronauts inside are also rotating in uniform circular motion, which means they need to have a normal force, okay, to supply that centripetal force. And that normal force ends up to be simulating the weight force on Earth. So the astronaut actually feels like there's a weight force, but it's only simulated. It's not a real gravitational field. Okay, so that just actually to explain it. So like as the spaceship is rotating, the astronaut in here also rotating. That means the centripetal force must be supplied by some real force, which conveniently is gonna be the normal force of the sort of the walls of this spaceship, right? But to the perspective of the astronaut, the walls are more like ground. Okay. So yeah, just argue your way through, talk about that. Okay. Yeah, so like on Earth, you have why we feel gravity is we feel this normal. And it's kind of equivalent in this case. So that's just like this logic here. Right. So you just make sure that the spaceship is rotating at some sort of velocity, right? So that this thing is like equals to mg, right? Does that make sense? Okay. So saying that your velocity is like fast to like certain value, and the size of the spaceship is like this r, is like just happen to equals to g. Like engineer would design this v so that this computes, and then if this happens, the astronauts would stand on the walls of this spaceship. Yeah, this is the wall, and then they will feel gravity. Okay. Question B. Yeah, so this one goes a little bit outside the syllabus. So it requires you to read a little bit of the extension material, especially on the further rotational object stuff. This question involves like how torques affects the rotational motion, and it involves something called the moments of inertia. Look, I still gave the equation here. So I think you can also do this question without actually reading or understanding the extension material. But it's essentially just substitution of values, okay? So torque in this case will be like a force that induces motion. Sorry, a force that induces rotation. So like force causes acceleration, torque causes rotational acceleration. So that this alpha is like a double derivative of angle. So it's like the acceleration of how how angular displacement is changing. And I here is like it's called moments of inertia, but it's just like mass, right? It's just like resistance to acceleration. Okay. Right, and then see how the angular velocity is kind of like this is v equals to u plus at, but it's omega equals to the initial angular speed plus alpha times t, right? It's like the same shape of equation. Mathematical symmetry is very strong in this case. Okay, so calculate the time required for the astronaut. So what's happening like is in the endurance, this thing has to accelerate to that velocity to simulate gravity, right? So asking about the time for like how long do I need to accelerate so that I achieve this speed? Okay. So first thing you need is to calculate what speed do I require, right? This is kind of sort of from the question A, right? And then just like do the rotational kinematics. Okay. I mean, this momentum inertia seems scary, but it's just a constant. Come on, it's just like a constant because I gave you the inner and outer radiuses. Okay, m is given as well, so that's just a constant. You can compute this and then treat it as a mass or something. Okay, all good. So you end up spending like almost 4 minutes. Okay, so that's like roughly like also shown in the video. Okay, so it's kind of accurate. Question 20. Oh, this question extends itself a little bit about like what we're gonna do for next lesson. Okay, on gravitational motion. Yeah, and then explores a little bit about torque and how you can use definition of torque to show that um, something interesting. Okay, with this orbital motion. So like this is like a planet orbit revolves around like a star, and gravitational force, of course, like it's this force that Newton discovered, not discovered, but like said something about it, and it's like every massive object has this force and it's attractive, and its equation is gmm over r squared. It's inversely proportional to the square root of radius or the distance between proportional to the mass. So show that the net torque on the orbiting object M is zero. So there's okay, even though the object is rotating and there's like a force that's forcing it to rotate, but there's no torque, right? So it's kind of difficult to show that. How do I show that? So we know that this gravitational force is like towards the center of, toward the center of the star, right? And then this radius is also like along this line. So it's kind of parallel. So FG is parallel to R. So if you recall how torque is like defined as this, right? You have to have a perpendicular component in order to have torque. But in this case, zero, so you just say zero, okay? So now if torque is equal to zero, right? If I tell you like this like a momentum about rotating objects equals to mr times v, it's called angular momentum, right? Show that the angular momentum is conserved, right? This thing is like linear momentum. It's like m times v. It's like for object going in like that straight line motion. There's also like a momentum for object rotating in circles, okay? And it's also conserved. Like we want you to show this conservative quantity. Mathematically, this means like angular momentum undergoes like rate of change with time is actually it's not changing with time. So like that thing is zero, okay, mathematically saying. So if you consider that, right? And we know that force equals to m times a, right, which is dv dt, okay, m times dv dt, and then torque is therefore r times f, which is m times a, which is m times dv dt, okay, and then which is r times m final velocity minus initial velocity. I just expanded out of it here, so nothing too complicated. Okay, I end up getting something like this, right? If I expand the bracket, but notice how this is just angular momentum, right? Okay, and factorize out r times m, you get that. Okay, notice how this is just like changing L. Okay, right? So, but torque was zero. That was just proven in part A. Okay, which means that the changing of angular momentum is zero. So now we have found something conservative for like gravitational motion, right? Which is very important because like if you think about how conservation of energy and momentum have helped us to calculate complicated collision problems and even like conservation of energy was so like useful in this question, right? And then we have just showed something else, like a new thing that is conservative. And there's gonna be very like useful aspect of it. And we're gonna actually discuss this in the future. Okay, so conservative properties are very important in physics, and I don't know, like basically the study of physics. 80% of time is to look for these conservative properties, and to prove that they actually conserve. And or if they're not conserved, we have to find out what ways, in what circumstances are they not conserved, and what consequences are these. Okay, so basically, conservative properties are very important. Okay. Yeah, the challenging question for this week is a bit involved. So if you have worked your way through up to this point, you have my respect. Okay. All right, enjoy physics, and I'll see you next time.